Continuing our discussion of drawing Lewis structures, we're going to take a look at a variety of examples. All right, so we can describe Lewis structures, we can go through all this process. And so we're going to be getting into Lewis structures of a bit more complicated molecules. And so what we're going to do is we're going to introduce an idea as to how we can kind of characterize these molecules that's going to come up again and again. And that's the idea of electronegativity. So when we started, I said that, we were sharing electrons in these bonds, sharing a pair of electrons. Well, it ends up electrons are not shared equally in a covalent bond. They are shared between the two atoms, but not necessarily the best. Some atoms pull these electrons more towards themselves. And we characterize this quantity, or this property, with a quantity called electronegativity. You can think about it as how strongly an atom pulls electrons towards itself in a covalent bond. Or another way, you can also say how greedy it is, right? How unequally shared it pulls electrons, right? And so fluorine, it ends up as the most electronegative element. Electronegativity is a property, as a periodic trend. It increases across periods and up groups. And so fluorine is the most electronegative. It has a value of 4. Cesium at 0.7 is really low. So when fluorine forms bonds, it's pulling those electrons towards itself. And anything that has a lower electronegativity will lose to it. So oxygen, being right next to fluorine, is the second strongest. So if oxygen's bonding with anything else, it pulls those electrons towards itself, but fluorine can even beat it. And so, one of the things about these trends is it's defined in such a way that it's the exact same as our ionization energy and electron affinity. So fluorine is the highest, that upper right corner is the highest, and it's the lowest in the bottom left. So if we look at, for example, hydrogen and chlorine, so say an HCl molecule, chlorine has a higher electronegativity. And so as a result, we can see here there are more electrons around the chlorine. That's kind of what that blue is indicating. The electrons are pulled towards the chlorine atom. They are not equally shared. It is important to note about electronegativity. This is not a measurable quantity. This is just a concept we made up. You can't measure whether or not a chlorine atom is not equally sharing electrons with a hydrogen. Sharing is an idea that we came up with as people, and so we just kind of put that on. So one thing that's important to note, this is just a property that people came up with to describe observed properties, observed trends in other things. Other properties that we will see down the road. But we know that electronegativity is useful, and as one of the important aspects of the fact we made it up is there's no exceptions. Everything follows perfectly. Things that have the same electronegativity or the trends are always going to be locked in. All right, so electronegativity is going to come up again and again, and we'll see it right here where it comes up the first time. So let's draw a Lewis structure for CF2O. This is a more complicated molecule than what we've seen previously, but let's see if we can use our technique or our algorithm, our approach, in order to come up with this Lewis structure. So step one is always how many valence electrons. And whenever drawing a Lewis structure, it doesn't matter how complicated it gets. For any molecule, the first thing you want to know is how many valence electrons. So there's 1 carbon, 1 times 4 gives me 4. I got 2 fluorines, each of those brings in 7, and the 1 oxygen brings in 6 for a total of 24 valence electrons. All right, great. Next question, which atom is in the middle? So when we followed this, we said previously it was going to be the atom in the front, and so we could probably look at that for carbon. Other rules we can use is we put the least electronegative element. So what is the furthest away from fluorine? So we're not going to put fluorine in the middle. We're not going to put oxygen in the middle. So that points to carbon as well. And we want to put also another good idea. If we think about that atom in the middle needs to form a lot of bonds. So we probably want to put an atom that's going to tend to form the most bonds. So carbon is in group 4. It needs 4 more electrons. All signs point to carbon as the central atom. All right, so just put carbon in the middle and draw lines to the others. Right, this is our Lewis structure, the same idea. Put that atom in the middle and draw the connections to the outer atoms. There's no bonds between the fluorines or the oxygen or anything like that, just all kind of a middle with spokes coming out. Okay, so I have assigned electrons. I need to account for them. I started with 24. I have put 6 in those bonds, giving me 18 electrons left. All right, so there's 18 electrons left. That is where I put lone pairs on my outer atoms. Each outer atom needs a full octet. So they all have single bonds. That's 2 electrons. They each need 6 more. So I throw the 6 more. They ends up with 3 lone pairs on each of my outer atoms. They now have full octets. Importantly, I need to account for that. I have used 18 electrons. There are no electrons left. I cannot, at this point in time, draw any more lines or dots on that Lewis structure without changing something. I can't just add more electrons to satisfy everything, right? I have used as many electrons as I can. All right, so now that I have a structure, I got octets on the outer atoms. I need to check the central atom. Does the central atom have a full octet? And the answer is no. That carbon does not. The carbon only has 3 bonds, that's 6 electrons. So if I have any leftover electrons, I need to add necessary lone pairs. In this case, I don't have any, right? This is where I don't have those leftover electrons. There's 0 electrons. I can't just draw in a lone pair. So I need to convert a lone pair from an outer atom into an additional bond. So we've done this before. We saw the nitrate example. And in that case, we pulled it from just one of the outer oxygens. But here I have a choice. Do I take that outer lone pair from an oxygen? Or do I take it from one of the fluorines, right? Which atom forms the double bond with the carbon? And the answer is I'm going to choose the outer atom with the lowest electronegativity. Well, fluorine has the highest electronegativity, so I'm going to choose the oxygen. So what I'm going to do is I'm going to take one of those lone pairs and turn it into a double bond. So now the fluorines keep their single bonds. The oxygen now forms a double bond with the carbon atom, and the carbon now has the 2 single bonds and the 1 double bond for a total of 8 electrons. All of my atoms now have a full octet, and I have obtained the Lewis structure for CF2O. So even though this isn't a truly binary compound, we can still use our approach to come up with the Lewis structure. And this is the right, correct, full-on Lewis structure for this molecule. So this approach will really help us, kind of piecing out what's the middle, what's on the outside, fill everything in. All right, so let's draw some more Lewis structures. I got SO3, Ch2 Cl2, NF3CS2. So again, overall approach is always start by calculating the total valence electrons. Right? This is why we've worked on valence electrons previously. This is going to be really important for determining how the bonds are going to form based on what you have and where they're going to go. Bond those outer atoms to your central atom, add lone pairs to the outer atoms till they're full, and add any extra electrons to the central atom as lone pairs. If you can't do that, make multiple bonds if the central atom lacks a full valence, right? If you don't have any more electrons to just throw on those central atom lone pairs, make some double bonds. Make those multiple bonds. All right, so Sl3 Sulfur Trioxides. We'll start with this. So I know I have 1 sulfur and 3 oxygens, so that gives me a total of 24 valence electrons that I need to assign. So I'm going to put sulfur in the middle because it's first. It's also less electronegative than oxygen. It's beneath it on the periodic table, so it has a lower electronegativity. So I got this nice little shape right here. And I want to start doing some accounting. I had 24 total electrons. I have put 6 into bonds, giving me 18 electrons left. Next, put some lone pairs on those outer atoms. Each oxygen currently has 2 electrons from a single bond, so they each need 6 more electrons in 3 lone pairs to give them a full valence. Account for that, so I need to subtract out those 18 electrons. There are 0 electrons left. Here's where I ask, is the sulfur atom have a full valence? No, it only has 3 bonds. That is 6 electrons, so I need to make a lone pair, or turn one of those lone pairs into a double bond off one of the oxygens. And since they're all oxygens, I can just choose whichever one I want. And now I end up with this. I take that lone pair and move it in to form a double bond. So the sulfur forms a double bond with 1 oxygen and then single bonds with the other 2 oxygens. And this is my Lewis structure of the SO3 molecule. Let's take a look at CH2 Cl2. So again, a little more complicated, but we'll see if our approach will work, even though it's not just 2 types of atoms. So it always starts off with total valence. 1 carbon, 2 hydrogens, 2 chlorines. Carbon has 4 valence electrons, hydrogen has 1, and each chlorine brings in 7. for a total of 20 valence electrons. So now the question becomes, what do we put in the middle? Again, carbon is written up front, so it's usually a good place to guess just carbon. The other thing is carbon tends to form a lot of bonds, namely 4 bonds with its 4 valence electrons. And so as a result, putting carbon in the middle is usually a good idea. Want to account for those we just added. 20 total electrons minus the 8 from those bonds gives us 12 electrons left. If we take a look, now we want to add some outer atoms, give them some lone pairs. So we have hydrogen and chlorine as the 2 different types. Hydrogen does not need lone pairs. Hydrogen only gets its 2 electrons. So those are actually done. The chlorine atoms definitely do want some lone pairs. They want that octet of electrons. They only have 2 electrons from the single bond as it stood. So we got to give them 6 electrons as lone pairs. If we account for those, we have 0 electrons left. So the hydrogens are okay with their single bond. The chlorines are okay with their 3 lone pairs and 1 bond. What about the carbon atom? All right, after we've assigned all of the outer atoms, return to the center. Well, that carbon atom is in 1, 2, 3, 4 bonds. We can see the 4 lines coming out of it. Each of those contains 2 electrons for a total of 8. So again, the carbon atom is satisfied with a full octet. So this is our Lewis structure for Ch2 Cl2. Let's do NF3. All right, count the total valence electrons. 1 or 5 for the 1 nitrogen, 7 each for the 3 fluorines, for a total of 26 valence electrons. Draw out our structure. Nitrogen in front means it goes in the middle. Nitrogen having single bonds out to the 3 fluorine atoms. Do some accounting here. From the 26 I started with, I have placed 6 electrons, giving me 20 electrons left. Time for some outer atom lone pairs. Each fluorine as it stands has the single bond. That's 2 electrons. They each need 6 more, so they all get 3 lone pairs. That's 6 electrons each. I just put out 18 electrons. There are 2 electrons left. So now I need to return to the nitrogen. Can I put those 2 electrons there? Yes, I can. Right? It had 3 bonds. Sorry, that was 6 electrons. 2 more in the lone pair gives it a total of 8. I assigned those 2. There are no more electrons left. Right? So this is then going to be the Lewis structure for NF3, nitrogen trifluoride. The nitrogen atom has a single lone pair and then 3 single bonds out to the different fluorine atoms. Each of them is then participating in that 1 single bond. Okay, CS2, carbon disulfide. Total valence electrons, what we start with, 1 times 4 from the carbon, 6 valence electrons on each of the 2 sulfurs, gives me a total of 16 valence electrons. Draw out my skeleton. The carbon single bonded out to the sulfurs. Account for that. 16 total electrons. I just assigned 4 to my bonds, giving me 12 left. Each sulfur atom needs 6 more electrons to give them octets because they only had 2 from the 1 bond. 8 total electrons on each sulfur atom now. Account for those, subtract out that. There are now no electrons left, so I cannot just add lone pairs. I can see that my carbon atom only has 2 bonds, no lone pairs, so that does not have a full octet. That needs some more electrons. I cannot just add lone pairs to that carbon, so I need to take lone pairs off of the sulfurs and turn them into multi-bonding. So what I can do is, I need to do it twice, right? So overall the carbon only started with 2 bonds initially. It needs 4 total. So what ends up happening is a lone pair from here goes down to form a double bond, and then a lone pair from over here also goes down and forms a double bond. So then the carbon atom is participating in 2 double bonds. Those 2 double bonds have 4 electrons each, so that's a total of 8 electrons. The sulfur atoms have a double bond for 4, and then the 4 lone pair electrons for a total of 8 as well. So carbon disulfide has carbon double bonded to the 2 sulfur atoms each. Okay, so overall, we kind of want to put into perspective all of these Lewis structures we've been looking at. And, one of the things is, we have all these processes for coming up with these structures, following algorithms, accounting. And when it comes down to it, one of the things we kind of want to start to develop is these ideas of how many bonds do atoms tend to form. We know that oxygen, is in group 6A, so is sulfur. They have 6 valence electrons. They need 2 more for a full valence, so they tend to form 2 bonds. Nitrogen and phosphorus in group 5A are going to tend to form 3 bonds, just like the fact that they form, they need 3 more electrons. Carbon, germanium in group 4A are going to tend to form 4 bonds, right? And so that idea, we can start to kind of pick up on patterns. So those are our central atoms we tend to see. If we look at the outer atoms, halogens are all group 7A. So fluorine, chlorine, iodine, bromine is not pictured. All just need 1 more electron, so they tend to form only 1 bond. You'll notice in all these, it's tending to form, right? These are all basic things, and in most molecules, this is going to work. We will see some exceptions will come up, but for the most part, there's tendencies to form. We can always predict what's going on, give us a gut idea as to what kind of shapes we're going to form. Our other main role is hydrogen, and hydrogen in this case is going to follow strictly. Hydrogen only needs 1 bond. It's only going to form 1 bond and no lone pairs. It's always going to be on the outside. It's kind of like decoration. If it can only form 1 bond, it can't be in the middle. It can't form a spoke. It can't have a bunch of spokes coming off of it. So you're going to have this, OH2 with the hydrogen on the outside, CH4 hydrogen on the outside. Those hydrogens are always kind of outside, satisfying 1 bond and no lone pairs. So we can kind of work, we have all these rules, and we can use those rules and build up our molecules, but we can also start to develop some ideas to what sort of bonding patterns should we expect.